In this video, we'll be looking at integrating some trigonometric questions or trigonometric identities. So, very first example is integral of tan square with respect to x. Tan square of x with respect to x. So, you may know that tan is sine over cos, but tan square will be sine square over cos square. That's not going to help us very much. Okay? So, another way to think about tan is that when we found some trigonometric identities, we identified that 1 plus tan square was sec square. So, but we don't have that here. What do we do then? If I ask you to pause the video and think of some trigonometric identities that involve tan square, which one can you think of? Tan square was in one of the trigonometric identities that we found in chapter 6. 1 plus tan square was sec square. So we can rearrange that identity and write tan square as another function of sec square. Let's go back to the original equation. We divided this equation by cos square and we ended up with tan square plus 1. So we can subtract 1 from both sides and write tan square as sec square minus 1. Putting that into this integral under the integral, we know that the integral of sec square is tan, and integral of 1 with respect to x will be simply x. Because it's an indefinite integral, we will add a c at the end. This next example involves both sine and cos of x multiplied together, and their inputs are a function of x itself. Luckily, the inputs both match and they are both 3x. So, first of all, let's deal with the fact that sine is multiplied by cos. If we replace z to be 3x, we can use this identity where we found the double angle formula for sine is 2 lots of sine by cos, but we are actually missing the fact that there is a 2. We are missing a factor of 2 under the integral. We can put it under the integral as long as we put a factor of a half outside the integral. And at the same time, we know the coefficient of x would have come out at the front if we differentiated that sine of 3x. So we have to also divide by a factor of 3. So we replace, in the first instance, we are going to replace sine of 3x, cos of 3x, with half of sine 6x. Okay? So let's put that there. We're going to do that. Okay, so integrating sine means that we are missing a factor of 6. If we differentiated 6x, we would have multiplied cos by a 6. So that's why we are going to put a factor of 6 also in front of the answer. So the final answer will be negative 12 multiplied by cos 6x. This question is asking us to integrate sec x plus tan x squared. So we are going to simply multiply out the bracket. We will end up with sec square and tan square at the end of the integral and 2 sec tan in the middle. Now, the fact that the order doesn't matter, we will get 3 terms because it's a trinomial. We are going to use the same trick that we did in our first example to get rid of tan square. We can replace tan square with sec square minus 1. Then we will have then we will have 2 lots of sec square under the integral minus 1. So the fact that there is two lots of sec square, that's fine. We factorize the 2 out and we know that the integral of sec square is tan. Therefore, we will have 2 tan for the first term, integral of the first term. Integral of -1 will be simply minus x because we're integrating with respect to x. And we have two lots of sec x tan x. So if you look in the top left corner, we have the derivative of sec being sec multiplied by tan. And luckily in our case, the coefficient of x is just a 1, therefore we don't need to adjust that. Anything else, we will simply keep the 2 in front and we will replace that term, the final term, with sec 2 times sec of x. And we will add a plus c at the end because this is an indefinite integral. Now in this next example, we have been told the answer to this integral, but we still have to prove it and show why it's the way it is. So we learned that some double angles can be rewritten in this form, and I emphasized there that we can replace sine square here with rearrangement of this equation. Because we have a sine square here, we can say 1 minus cos of 2x will be 2 lots of, if I rearrange this equation to make sine square the subject of the formula, I will have 1 minus cos of 2x here, and dividing both sides by 2, I will have sine square of x equal to half multiplied by 1 minus cos of 2x. This is, believe it or not, a much simpler way of integrating sine square. So what we get is this expression under the integral. Then we can integrate with respect to x. Half will give us half of x. Cos of 2x will give us a sine. Negative cos will give us negative sine. But because of the input, the derivative of 2x is a 2, we will have to multiply a half with another half. Therefore, we will get negative half sine 2x as the answer. Notice, once you do integrate, you do have to drop the integral sign, and now those limits of the integral, pi over 8 and pi over 12 will go, we usually write them at the end of the square bracket on the right hand side. Now we're going to substitute the upper limit of pi over 8 first and subtract the expression when the lower limit is substituted into it. We can keep the half as a factor on that side of the bracket, and simply putting these into our calculator, we'll end up with these answers here. And finally, the final answer should simplify after some manipulation and getting common denominators. We will end up with what the question gave us. Pi over 8 and pi over 12 can get a common factor of 48 inside the bracket, and the other two fractions have factor of 4, so subtracting and adding them with each other will give us 24, and multiplying half into it will give us a denominator of 48 and denominator of 8. Okay, so that was the final example here. I see you in the next video.